Okay, so this video is about thermodynamics. It's a crash course. It's most useful for students who are doing this standard here, particularly those students who are sitting their exam in a few days. If you're wanting a more advanced thermodynamics course, we'll be doing that a bit later on, but this is really just a lot of stuff that we need to get done for this paper here. It's in a couple of days as I record this. So a couple of things that we won't be doing much of. We will not be doing much of what's called thermal expansion, which is things sort of expand as they get hotter or colder. It's not really covered that much in the curriculum, so we're not going to cover it, but we're gonna mention it in passing. So this guy up here is Lord Kelvin. He is the guy who gives his name to the temperature scale, which is used in science. He has a rather amazing contraption here, kind of a steampunk thing. I think it's his first thermos flask. So it's a vacuum vessel. So in the middle here is a container, and on the outside is a sort of container outside that container, which is full of a vacuum, so full of nothing essentially. And what he discovered, he used that he could fill that with water, and he could work out how energy and heat conducts and how it works. And he's really considered the father of thermodynamics. But that's the end of the history lesson. Let's get on with the science. So the first distinction that we need to make is the difference between heat and temperature. You might think that they're synonymous. They're kind of synonymous, and you kind of intuitively know what heat is. I think it's one of the things that you're born with an innate ability to know when it's hot and when it's cold. So heat is thermal energy. So it's a type of energy, and because it's energy, it has to conform to the laws of conservation of energy and all the other equations that we use. Temperature is the measurement of thermal energy. So you might be thinking that this is the same thing, but really what we're measuring technically is the average internal energy of a system. So if we imagine a container in here, it's not going to be a uniform temperature, but what's going to be creating heat is the particles inside it. So say we have a really simplified container. The velocity and the energy in which these particles are bouncing off the wall and hitting each other is what really energy and temperature and heat is. So they're kind of the same, but there is a distinction, and it's often asked in exams, what's the difference between heat and temperature? You kind of intuitively know that when the temperature is low, there's not much heat. When the temperature is high, there is a lot of heat. Okay, so that's the basic distinction. So what do we measure temperature in? Well, in NCEA 1, we measure it in degrees Celsius, which is what we measure most temperature in. It's what you get the weather report in, at least if you're not in the United States, in which case you use the Fahrenheit scale, and the United States is pretty much the only country that uses that. The way that that's worked out is it was worked out by a guy called Mr. Celsius, and he bluntly said that we're going to set 0 degrees Celsius at the freezing point of water. So when water becomes ice, we're going to say that's 0 degrees. And then he said, okay, we're going to set 100 degrees to be the boiling point of water. And I should add that that's sea level under normal conditions. And then he said, okay, so what we're going to do then is we're going to sort of divide it up into single degrees. And in NCEA, we're going to call that change in T. So I guess another distinction we need to make is in physics, and especially in this curriculum, T is temperature, little t is time. Okay, so you can theoretically have the change in temperature given a change in time, T over T. So to get around that, we have capital T for temperature, lowercase t for time. So this is the scale that we're going to use in this curriculum. From next year, you'll be using the Kelvin scale, which is the SI unit for temperature. And what Kelvin scale does, it takes 0 degrees Kelvin is what's called absolute zero. And it is the coldest temperature which you can possibly get. You can't get any colder than absolute zero, and it is debatable whether it's actually possible to get absolute zero. We've never actually got anything that's at absolute zero. We can get pretty close to absolute zero. Absolute zero is really, really, really cold. 0 degrees Kelvin is approximately equal to minus 273, I think 0.15 degrees Celsius. So really, really, really cold. Most things in the universe are actually kind of below what we would consider cold. Our planet is relatively warm. The way that he works this out, though, is he uses the same scale. So a change of 1 degree Kelvin is equal to a change of 1 degree Celsius. So 0 degrees Celsius is equal to 273 degrees Kelvin, and 1 degree Celsius is equal to 274 degrees Kelvin. It's on the same scale. Fahrenheit is not on the same scale. Do not use Fahrenheit. If you're given Fahrenheit, you need to change it. It's definitely not part of the metric system. So that is absolute zero. That is temperature, the difference between temperature and heat. So with that, let's move on. So the first rule, heat moves from hot objects to cold objects. It's a form of energy, so we cannot say that if we have a hot object that it gets coldness on it. It loses heat to a cold container or something colder. The heat moves in that direction, never the other way. So what that means is that if we have, say, a room, here is some container, and let's say in this container there is water, H2O. Okay, and we have this water, let's say it's at 10 degrees Celsius. And into that we place a really, really, really hot object, say iron, and let's say this iron is at 150 degrees Celsius. What's going to happen is that the heat from the iron is going to move out of the iron, so the iron is going to cool. It's not going to take in coldness. It's going to move out in every direction that it can move away from the iron into the water. So what's going to happen is that the temperature of the iron is going to go down, and the temperature of the water, H2O, is going to go up. It's not going to be a one-to-one basis, but at some point they're going to be the same temperature. And we call that thermal equilibrium. So nature loves equilibrium, and it will tend towards an equilibrium, which is when these things are the same temperature. Now, obviously, the water is not going to go to 120 degrees because it would turn to steam. The iron is probably going to be fairly close to the 10 degrees than the water is to the 150, because there's a lot more water than there is iron. So the mass matters as well. So let's say after a long time, the temperature of the water may be, say, 15 degrees, and the temperature of the iron will be 15 degrees, because they will be the same temperature after long enough, presuming that there's no heat coming from outside. So there is no coldness going into the iron again. The heat comes out of the hotter object into the colder object. In a way, we can kind of think of thermodynamics as there's no such thing as coldness. We can think of coldness as an absence of heat, in the same way that we kind of think of the color black as kind of an absence of light. Coldness is an absence of heat. All right, next rule. No process is perfectly efficient. We always lose some energy. All right. Well, we'll get to that in the next one, but we will never convert 100% of what we want from what we started with. So say we had a ball at the top of a building and we dropped it. The theory is that the potential energy at the top must equal the kinetic energy at the bottom. It's not quite true. There's always going to be a little bit lost to heat or sound or something like that. There is always friction. There is always some loss of what we want. So no matter what type of vessel we have, if we have a thermos flask and we put a hot liquid into it and seal it up, we're never going to keep all of the heat in. We're always going to lose a little bit. And eventually those little bits will add up and the heat will be lost, regardless of how good our flask is. There is no such thing as a perfect process or a perfect piece of apparatus. We always lose something, and the technical term is there is always entropy, which basically means we lose things because of friction mainly, or inefficiency. We cannot avoid entropy. It's a big thing later on if you decide to continue doing physics. But just for now, note that is something which pops up again and again and again and again in exams. The last two exams in this topic have pretty much asked the same question. we started with this amount of energy, we ended with some other amount of energy. Why is what we get slightly less than what we started with? Well, we lost some of it because of heat or something like that. So let's say we have a container of water. So we have some water here, and we put a filament in there, and we run a battery through it so that it goes to heat that water up. The energy from the battery here will never completely go in here because we have wires here that are going to heat up ever so slightly. They're going to lose a bit of energy, and the filament is never going to be perfectly efficient. It's going to be pretty good, but it's never going to be perfect. So if you end up with more energy than we started, you've made a mistake. Okay, the third rule is the conservation of energy rule. What that says is that we cannot make or destroy energy yet. We can kind of do it using Einstein's theory, equals mc squared. We have relativity, but you won't get that till year 13. For our purposes, we're going to say that you cannot make or destroy energy. You can only change its form. Okay? You can only change the type of energy. And I'm going to illustrate that by using a simulation from Phet. And I'll put the link in the description. So here we have a simulation. We have this person here on an exercycle. The exercycle isn't going anywhere, so why she needs a helmet, I don't know. What's going to happen is we're going to run the simulation. So she's going to start pedaling the bicycle. The bicycle is going to turn this wheel. This wheel is going to generate electricity. The electricity is going to go into this resistor here, this basically a kettle, and it's going to heat up the water. So I'm going to put the symbols in so you can see what's going on. I have a problem with this because it kind of violates the last rule that I just described, where everything is perfectly works perfectly. So in here we have chemical energy in the girl here. So she is converting chemical energy. So she would have eaten some food, and the food would have come from the sun, from plant matter. She's converting this chemical energy, chemical potential energy, into kinetic energy here on the bike, which is moving this generator. Here is mechanical energy. The generator is generating electrical energy, which is blue. The electrical energy is making thermal energy, heat energy here. You can see that. And the heat energy is leaving the atmosphere. So this thing is getting towards equilibrium. The water is moving towards the same temperature as the metal that's in here. I forget the name now. And she has run out of chemical potential energy, and now this water is going to cool down. There's nothing going on, and all the heat is dissipating into the atmosphere. Okay, if we give this girl more food, she's happy again. We give her chemical potential energy. She converts it to mechanical energy, the grey bit here, which becomes electrical energy, which becomes thermal energy. It's just energy to energy to energy to energy. We're not making energy, we're not destroying energy. Let's change it. So I'm sick of looking at her.
let's say we are now having solar energy. So now there is yellow E, so there is light energy. And notice that nothing is happening. A generator cannot convert light energy into kinetic energy. It can't therefore convert that into electric energy, and it can't convert that into heat energy. But if we change this from a generator to a solar,
then the light energy is being converted to electrical energy, which is being converted into heat energy, which is now leaving into the atmosphere as these become the same temperature, they reach their equilibrium. So if you change it to a light bulb, this other thing going on. So light energy from the sun, solar panel, converts to energy, electric energy, starts energy, which turns that into energy. If we light bulb use, we can say that the light energy here is going to light energy comes off. That's because the solar panels on the temperature, we're going to lose heat away, we're going to lose heat into bulb, we're going to lose heat comes off the light bulb. If you can see, sometimes here, heat comes off, so we see energy. You don't really do much installation here, energy still applies. All right, the next rule 4. Most substances expand as they heat up. So if we have a piece of metal here, let's say iron or steel or something, and we put some heat into that, so we make this hotter, this is going to want to expand outwards. And it wants to expand outwards because the particles in there have more energy and they want to push each other further apart. So it's a bit of a problem when we come to use engineering. We have to sort of take that into account. And the classic example is if you look at train tracks really close up, if there is a train track here, so here's the track. In between the tracks is going to be a little gap. So obviously this is my terrible drawing. There is going to be a little gap between these tracks. And the reason that there is this little gap here is that in a hot day, this is going to expand. So if there wasn't a gap here, these rails are going to push into each other and it's going to warp. So I'm going to put a picture of what happens if there isn't a sufficient gap in a railway line right now. So this expansion, its thermal expansion, is most dramatic when we have a change of state. So in other words, when something goes from being a solid to a liquid to a gas. So for most materials, when they convert from being, especially from a liquid to a gas, the gas wants to occupy a lot more space. There is a lot more energy, and the bonds between particles breaks down. They want to push each other apart. They want to take up more space. So if we don't increase the space, the pressure must increase, and we can exploit that. If we have an engine here, for example, and we put water in here, and underneath that we put a fire, and we heat that up until it becomes steam, we can use that. So we can let the pressure build up, and then if we allow some of it to escape, it will want to go into more space, and that pressure we can use to turn a turbine to make electricity. And this is essentially how a steam engine works. And in fact, a nuclear power plant pretty much is just a really elaborate steam engine. Instead of fire here, there is uranium 238 mainly for reactors, and uranium 235 in a reactor. We let that become slightly unstable. We don't let it have a runaway chain reaction, but it creates enormous heat. The heat heats up water, and actually in a nuclear power plant, the water heats up a system of water. It exchanges the heat from here into the water, becomes thermal energy, which then becomes electrical energy. It's a bit like the simulation that we just had. This is the same way that your car works. So in a car, an internal combustion engine, we have a cylinder here, and we put liquid in vapor form into it, and then we light it. So we increase the temperature rapidly, and it wants to expand. It wants to take up more space now that it's hot, and that creates pressure, and it pushes this piston down, and that drives the engine. So it's kind of the basis of our whole Western society. It makes electricity, and it makes mechanical energy. So you may be asking yourself, I said that most substances expand as they heat up. Silicon does not. Silicon, when it goes from a liquid to a solid, actually expands. But the most important one actually is water. Water actually expands when it becomes a solid. But there's another slightly different reason that it expands. It becomes a crystal. So the water molecules want to create, if we imagine the H2O, they want to create a lattice, and they do that, and by doing that, it actually takes up more space. The weird thing with water as well is that when water is a solid, it's ice, it wants to increase the area that it takes up, the volume that it takes up. When it's a liquid, it decreases, but then when it becomes a gas, as we saw with steam engine, it wants to take up a lot more space. It's a really, really odd one out, but it's really, really, really useful property of water. When it's a solid, it expands. When it becomes a liquid, when it melts, it contracts, and then when it becomes a gas, it expands. We can exploit that really, really nicely. All right, rule 5. Heat can transfer three ways, remembering that heat always goes from something hot to something cold, or something with a higher temperature to something with a lower temperature. The first way that it can move is by conduction. So conduction is when heat moves without particles moving. Okay, so this really only applies to solids. So when you get to university, maybe even in your school later on, you'll do the following classic experiment. You will have a really, really thick steel bar. So here we have the steel bar, and you have a thermometer. So you'll probably have one of the optic thermometers, and you can take the temperature on any part of this solid bar. So let's say it's 2 meters long. What's going to happen if we take a blowtorch and apply heat here? So we have a sort of some blowtorch gun, and we basically heat up this end. What's going to happen is that the whole bar is not going to heat up straight away. Eventually it will. What's going to happen is that this end here is going to heat up first, and this heat is going to gradually move down the bar. So it may be some time before this end of the bar, we have a sort of a little thermometer here, before that end is as hot as this end. And it will just heat up until it melts. And in fact, probably this end would melt first before this end, because this end is going to get hotter faster. So heat moves through solids through conduction. So we can exploit things that conduct heat. I mean, your frying pan is great. It works because it conducts heat. We can put heat in it and the heat will move down a solid. We can also use things which are insulators. So insulators are things that do not conduct heat well. Everything conducts heat to some degree, but some things don't conduct well. And glass is not a good conductor of heat. Wood is not a good conductor of heat. There are a couple of things that aren't really good conductors of heat, but those are the two ones that we want. A lot of plastics also do not. Plastics and ceramics don't conduct heat very well. And that's important because if we get back to our frying pan, if we have our handle here that goes into the frying pan. So again, I'm not an artist. I cannot draw to save myself. So this is the metal bit. This is the handle here. And let's say that's a wooden handle. It looks more like a knife than a frying pan. And we have heat here. The frying pan itself is going to get hot, but this is not going to get as hot. Certainly nowhere near as hot, and certainly nowhere near as quickly. And that means that we can hold the handle here, but we can't hold the pan. The pan is going to be made out of metal. Most metals are really, really good conductors of heat, the exception being lead. Wood is not a good conductor of heat, so this is going to get hot, and this is not going to get hot. Okay, so that's the first way that heat can move between objects. All right, the second way that heat moves between objects is by convection. So convection is when hot substances move into colder substances. Thereby transferring heat from the hot substance to the cold substance. So if you have a glass pan and we put water in it, and then we put it on an element on your stove, and we turn the element on, what's going to happen is that the water down here is going to get hot first. But then this hot bit is going to move up as it wants to occupy more space. So heat generally tends to rise, and we're going to see sort of currents of hot water moving. And if you sort of have a look at it, you can kind of see these hot eddies moving through a liquid, and it's convection. Convection really only applies to liquids and gases. And really it's the basis of whether heat transfer between objects. So that's one way of thinking of convection. The other way of thinking of convection is by thinking of kinetic theory, which is what we're going to get to now. And I'm going to use another Phet simulation that I'll put the link in the description. Okay, so here we see a container. The container is set up. It's a phony container, but it's a nice kind of way of thinking about it. In this partitioned part of the container here, we have 50 particles of some substance. We don't know what it is, but I've set the temperature there at 50 degrees. Okay, but what happens if we don't want heat to spread? Well, we can take our cue from Lord Kelvin in the beginning here by having a vacuum container. So vacuum is Latin for emptiness or nothingness. And what a vacuum container is, and you probably have one in your backpack these days. I've noticed a lot of kids have them. Certainly if you go to McDonald's, they have a kind of crude vacuum flask. What it is there is an outer container here, and that's there like that. And then there is a sort of inner container that's inside that. And what that does is if we put something hot in here, it cannot kind of conduct across. There are no particles there to hit. So here are the particles, and they're hitting here, and some of them may, if there were particles there, it would cause particles that were in there to move and hit the other side. But if there's no particles there, there's no way to propagate this heat. So if you go to McDonald's and you order a coffee, you'll notice that it's kind of squishy if you hold it. And there's two reasons why they do that. And at the bottom there is a kind of a gap there as well. So that's there for a similar reason. The reason that's there is to keep the coffee hot. Or if you have something cold in there that you want to keep cold, to keep that cold. So to stop heat from entering. The other reason as well is that we don't want the cup to get hot. We want the coffee to be hot, but we don't want your hands to get hot. So you can walk around with a hot coffee and not burn your hands. It's a really, really important concept, and you will probably have a question on this in the exam. If I have time to do the exam, we'll do that question. All right, the final way that we're going to look at how heat transfers is by radiation. So heat can transfer through the electromagnetic spectrum. Electromagnetic waves, really. Okay, so don't be scared by radiation. Radiation just means transfer of heat through transfer of energy through electromagnetic waves. It's really, really, really important because of the sun. Up in the sky, there is the sun. That's as good as I can draw a sun. There aren't particles of the sun hitting there. Well, there are, but not for our purposes. It's the heat is an infrared and an ultraviolet, and it's moving through space until it hits us. So it is kind of moved through electromagnetic radiation. So here's the Earth here. The heat energy, infrared, mainly hits the Earth. Some of it gets through. Thankfully, all of it doesn't get through, and it heats the Earth up, and we get to live. If you have a heat lamp, you can sort of buy those really, really bright lights, and it will transfer heat through radiation. You probably will not be required to know much about that, but it is the third way that heat can be transferred. So it can be transferred again through conduction, which is when it moves through a solid without particles needing to move. Through convection, so the liquid or gas will itself move, or the particles will move, or it can move through radiation. Okay, And always, always remember it transfers from the hotter substance or hotter body to the colder body, the body with less energy from the hotter, more energetic body. So now we get to the topic that a lot of students find kind of confusing, and it is the topic of heat capacity. So there are two types of heat capacity. The first one is called the specific heat capacity. Okay. Sometimes it's called the sensible heat capacity, but for our purposes, we're going to call it specific heat capacity. That's what your exam will refer to it, so I'm going to call it that. The other type of heat capacity is latent heat capacity. Okay. So for us, I want you to think that these are not the same and they're not related. They are independent of each other. Later on, that kind of breaks down, but we'll deal with them separately. Okay, let's have a look at specific heat capacity. So in the exam, you will have the formula that they will give you will be in this form. E thermal equals MC delta T. Okay. So E thermal is basically the heat energy. Right? So that's going to be measured in joules. If it's not in joules, you need to convert it to joules or kilojoules, 1,000 joules. That's going to be equal to the mass of the object that we're trying to increase. So that has to be in kilograms. I'm going to get to the C a little bit later because that's the bit that I'm really interested in. Delta T, delta means change, capital T means temperature. So this really means the change in temperature. So notice that it's not positive or negative. So the thing that I want you to sort of realize is that it takes the same amount of energy to increase the temperature of a substance as it does to decrease it. So if we have a substance and it increases in energy, it increases in heat, the energy that has to enter it to heat it up would, by say 5 degrees Celsius, would be the same amount of energy that would leave it if we decreased it by 5 degrees. So it's just change. So it's just the absolute value of the change. That can confuse a lot of students. If you have that as a negative number, you're going to get negative energy. And if you get negative energy, you'll know that something is going wrong, where we're not Stephen Hawking. We're not dealing with dark matter or dark energy or antimatter or anti-energy just yet. Okay, this is only NCEA 1. All right, the C bit here. So the C bit only applies when we're changing the temperature of a substance. Okay, and C is called the specific heat capacity of a substance. and it's different for every substance. So what that is, I'll give you the sort of formal definition of what it is. So it's the amount of energy, really we're talking about thermal energy, heat energy required to heat or cool 1 kg of a substance by 1 degree Celsius. All right, so run that through your mind so you kind of work it out. So if we want to raise the temperature of 1 kilogram of substance by 1 degree Celsius, the C is the amount of energy that we need to do that. And if we want to cool it down by 1 degree, that's the amount of energy that we need to take out of 1 kg of that substance. Okay, so I'm going to put up on the screen last year's question because they give it to you. Okay, so this is last year's exam paper. You can get it online. I'll probably leave the link. But the thing that we're interested in is this number here. You notice it's a pretty big number. So if we have 1 kilogram of water, so by definition that's going to be 1 litre of water. So we have 1 kilogram of water, so we have our flask here, and we have our water. And say this water is at 10 degrees Celsius, and it is 1 kilogram of water. Say we want to increase the temperature of that water to 11 degrees Celsius. We need to put in 4,200 joules of energy from somewhere in order to do that. That's what that means. Okay, so let's say we've got our bottle here and it's 0.75 kg of water, and we want to raise the temperature from 10 degrees Celsius to 20 degrees Celsius. First thing we've got to check is this going to change state? And if it changes states, we have to sort of stop and do something else we'll do next. And most of the time, water is not going to turn to steam if we increase it from 10 degrees to 20 degrees Celsius. It might if we were at really, really, really high altitude, but for us, we're going to say it's going to stay liquid water. It's just going to get hotter. How much energy are we going to need to put into that? So we have our bottle here, and again, as always, I cannot draw. All right, so we know that E thermal is MC change in T. The M is going to be 0.750. The C, the specific heat capacity, is 4,200 joules. And the change in temperature from 10 to 20 is 10 degrees. They're all in SI units, so I'm not going to put the SI units on there. How much energy are we going to need to use? Well, let's grab the calculator. So 0.750 times 4,200 joules times 10 degrees. So we need to put in 31,500 joules. Or 31.5 kilojoules, really. Which is quite a lot. It takes quite a bit of energy to heat things up. Different things have different heat capacities. Some things heat up really, really easily, and some things heat up really, really slowly. They require enormous amounts of energy. This is a really, really important concept to grasp. If you can kind of grasp this, you're kind of 80% of the way along. Notice it's linear. So if we did a graph, and this was time on this axis, and this is temperature, it's going to, over time, if we heat it up, if we apply the energy evenly, it's going to be kind of a straight line. As long as we put the energy in a predictable manner. So if we really wanted to do that, really the temperature and the energy, they're going to be like that. There's going to be a positive correlation, and it's going to be linear, mostly linear. All right. Okay. Now we get to the topic that really confuses a lot of students. All right. Now we get to the topic of latent heat capacity. So latent heat capacity is different from specific heat capacity. Latent heat capacity is given as this formula. ML. L is the latent heat capacity. M is the mass. E thermal is the same. So this is going to be in joules. This is going to be in kilograms. And this is going to be kilogram joules. All right. What does this mean? This is the energy required to change the state of 1 kilogram of a substance to another state. At freezing temperature or vaporization temperature. Okay, what do I mean by that? So let's come back to our water example. So we have some water here, and let's say we have a liter of water, and it is liquid water. Okay, and we want to turn it into ice. What are we going to need to do? Well, we're going to need to do two things. First thing we need to do is we need to remove enough thermal energy from the substance to bring it to freezing temperature, which for our purposes, we're going to say it's 0 degrees Celsius. Okay. Now, once we've done that, it doesn't just automatically become ice. We have to take out a lot more energy in order for it to become ice. And once it becomes ice, it will then start to go down in a linear fashion. All right, so if we did that on a graph, So here is 0 degrees Celsius, and this is time, and we're taking energy out of the water. Okay, so when we start off, it's going to start losing energy, losing energy, losing energy until it gets to freezing point, and then it's going to level off until we take out energy, and then it's going to freeze, and then it's going to start losing energy again at that same rate. Okay, now that energy is often really, really big. So often there can be a really, really big time gap between when it hits its freezing point and when it actually freezes. And in the meantime, it stays in the state that it's already in. Okay, that's if we wanted to cool it. If we wanted to melt it, the good thing is that it takes exactly the same amount of energy to freeze it as it does to melt it. So if we had a block of ice, a 1 kg block of ice, okay, so we've got ice and it's 1 kilogram. What do we need to do? First thing we need to do is we need to bring it from whatever temperature it is to its melting point. Then we need to apply the same amount of energy that it takes to melt it. So if we melted the ice, and here it's going to be 0 degrees Celsius. So here the ice is increasing in temperature until it reaches melting point, and then it's going to even off until enough energy goes into the ice, and then it's going to melt and then increase again. This is what killed the Titanic. This is why we have icebergs. Even though icebergs are floating around in water which is above freezing, the water doesn't have enough energy to melt it quickly. So something will stay a solid, it will stay ice if it's water, even if it's surrounded by something which is above its melting point, until it has enough energy to overcome that barrier. And that barrier is reliant on the latent heat energy. The latent heat capacity, I should say. All right. Now, there are, just to confuse things a bit more, there are 2 types of latent heat capacity. So there is the latent heat capacity, of fusion, and the latent heat capacity, I'm going to HC, of vaporization. So this is the energy required to melt or freeze a substance This is the energy required to convert from liquid to gas and vice versa. right? They are often not similar at all. It often takes a lot more energy for one of them than the other. So let's kind of take an example of our block of ice. So along here we have the time, and along here we have the temperature, capital T. Okay, time and temperature. And here we have 0 degrees Celsius, and here we have 100 degrees Celsius. And we start off with 1 kg of ice. And we want to turn it into steam. You can kind of go straight from solid to gas, but not until year 13. We need to go through liquid first. So we're going to start here at a freezing temperature. So here, as we heat it up, and in this part here, it's MC change of T, which is running things until it gets to melting point, and then it's going to flatten off until it gets enough energy to overcome that, and then it's going to increase at the same rate until it gets to its vaporization point, until it boils, which is at 100 degrees, and then it's going to flatten off again. So here is MC change in temperature, and here is the latent capacity of vaporization, and then it's going to increase again. It's not going to be a straight line, it's going to be kind of stepped. All right, now if we have steam and we want to turn it into ice, the opposite is going to happen, and it's going to take exactly the same amount of energy, except now we're not going to be putting the energy into the water. We're going to be taking it out of the water. So here we have 100 degrees Celsius, and here we have 0 degrees Celsius. So up here we have steam, and then it hits 100 degrees, and then it's going to flatten off until we have enough energy to condense it into water, and then it's going to go down like this until it reaches freezing point, and then it's going to level off until we have enough energy to freeze it, and then it's going to keep decreasing in temperature. So up here is gas, here is liquid, and here is solid. So in other words, steam, liquid water, and ice. We're going to do some examples of this a little bit later on. I think we've done enough for now though, and that's really all that I wanted to cover. We'll do some examples a wee bit later on in the next video. Until then, remember, physics works.